So today I am explaining from your page 67 galvanic cells. First I will explain this, and from here we will go to the Nernst equation. So I have drawn the Daniell cell. So in the Daniell cell, you know very well, this is how it looks like. The diagram is there in page 66. You can see a zinc rod dipped in zinc sulfate solution, and this zinc sulfate solution will always refer to as Zn2 plus aqueous. Then in the other container we have a copper rod which is dipped in copper sulfate solution, and copper sulfate we will always write it as Cu2 plus aqueous, and we have as usual the salt bridge connecting the two solutions, and these rods are connected to the battery. So when this cell starts working with the help of this electricity, it gives us this particular equation Zns plus Cu2 plus aqueous, giving us Zn2 plus aqueous plus Cus. So you see, this is the entire equation for the entire cell that is working, but separately something is working out here and separately something is working out here. So since zinc is in zinc sulfate, so there is a connection between these two. So what can we write from here? Zn S is giving us Zn2 plus aqueous. So how will a neutral metal atom get converted to Zn2 plus? Two positive charges means two electrons have gone missing or has come out. So we write minus 2 electrons. Then here in this container, what is happening? You can see from the equation it is Cu2 plus. So that means there is a connection between these two. So Cu2 plus aqueous is getting converted to Cu solid. So how is this happening? Because this is releasing out two electrons, the two electrons are going through the wire to this side and then getting picked up by Cu2 plus ions which are present inside the solution, remember? So it's picking up two electrons and getting converted into this Cu solid. So copper rod will get fatter because of the deposition of copper solid, and zinc rod will become smaller because zinc solid is getting converted into the solution as Zn2 plus. This is what is happening. So since there is loss of electrons out here, this is oxidation, and since there is addition of electrons, this is reduction. So this reaction is a redox reaction. If one does not occur, the other will not occur also. So this is a redox reaction. Now since here oxidation is occurring, so this portion is called the anode. So this side, that means, is our anode by convention because it is losing electrons, and this one will be the cathode because it is picking up to addition of two electrons. So this side is our cathode. Now when all of these things are going on, a potential difference is developed between, you can see the explanation is there in, the written portion is there in page 67. I am just explaining to you. A potential difference develops between the electrode and the electrolyte, which is called this particular potential difference is called the electrode potential. So between this rod and this electrolyte there is an electrode potential. Between this rod and this also there is a potential difference, so that is also called the electrode potential. Now if the concentration of this particular solution which I am preparing, if it is unity, means say 1 molar solution or 1 molal solution, in that case means I keep it 1 in whichever way I measure, as a molar solution or as a molal solution, in whichever way, but the concentration is always 1. In that case, once we measure these electrode potentials between the rod and the electrolyte, that electrode potential will be called the standard electrode potential. If we keep the concentration of these two electrolytes as unity. Then where the negative potential is developed, when reduction is occurring, that is called the cathode. Where oxidation is occurring, that is called the anode. So this much we can say about the Daniell cell. So I hope you have understood all this. Now, taking the help of the Daniell cell, or taking the equation of the Daniell cell, I am going to explain to you what is the meaning of cell electromotive force, or EMF. How to calculate. Now, how will we calculate? We said already that this electrode in connection with the electrolyte gives you electrode potential. This electrode also in connection with this one will give you an electrode potential. So when we want to calculate for the total cell, it will be E of the right side minus E of the left side. So this is the way we calculate EMF, or this is also called E cell. And if we calculate with respect to standard electrode potential, this will be called E0 cell. So it will be E0 right minus E0 left. So whenever we put the not sign, it indicates it is standard electrode potential. Now, instead of writing like this, we could also write either E cathode, because you know the right sided one is called the cathode and the left sided one is called the anode. So we can write E cathode minus E anode, or E0 cathode, E0 anode. This is also another way of representing it. Now, in a Daniell cell, which is the right side and which is the left side? The left sided one is zinc in connection with Zn2 plus, and the right sided one is Cu in touch with Cu2 plus. So we can also write E Cu2 plus slash Cu minus E Zn2 plus slash Zn. This is also another way in which we can represent it. Or you know, when we put the knots, what does it mean? It means standard electrode potential. Standard electrode potential means when we calculate the electrode potential when the concentration terms are unity. So this is the way of calculating either E cell or E0 cell. Then for a Daniell cell, the value comes out to be equal to 1.1 volt, or it's also written as 1.10 volts. This is the value which comes out from the Daniell cell. Then with the, what are the things that are there to be known? Now next we can calculate Nernst equation. What is this Nernst equation? Suppose you have an electrode, separately we will take. Let us take this one. Suppose we take where one container is there, rod is in connection with the electrolyte. Then in that case, this will be our M, which is in the solid state, and in the solution we have Mn plus, because copper or zinc always forms Cu2 plus or Zn2 plus. For a general one, we write like this. So if we take a general equation, Mn plus aqueous plus n number of electrons it will take up, and it will become solid. So how to write down the Nernst equation in such a case? So Nernst equation is written in this way: E Mn plus slash M is equal to E0 Mn plus slash M minus RT by NF ln. Ln means natural logarithm, means log. In maths you must have done. There is a log with base E and a log with base 10. log base E is represented as Ln. So Ln, concentration of this metal which is in the solid form, divided by concentration of this Mn plus in aqueous form. Now always remember, concentration of any solid is taken to be unity. So this goes missing and we write 1 out here. So this is the Nernst equation for a general reaction like this. So how can we write the Nernst equation for a Daniell cell? So you just remember, this is the this is the general equation, Nernst equation. Now we will take the help of, okay, let me write it here again. Let me write the general Nernst equation on top so it will be clearer to you. So you have E cell is equal to E0 cell, okay, to be more precise, general one, since I have taken Mn plus slash M, so Mn plus slash M minus RT by NF ln of 1 divided by concentration of Mn plus. This is the general Nernst equation. So we will apply now to the anode separately and to the cathode separately. Remember, this equation is for only one container. So let us see what is happening at anode. At anode, what are we having? Zinc solid in touch with Zn2 plus aqueous. So how will we write this? E Zn2 plus slash Zn is equal to E0 Zn2 plus slash Zn minus RT divided by, now you see it was 2, then N is the number of electrons, because if you remember, Mn plus N electrons, this is aqueous, gives you M solid. So there N is the number of electrons. So in the case of zinc, we will take it to be 2. So that's why by 2F ln of 1 divided by Zn2 plus aqueous. This is the way then the Nernst equation will be applicable for the anode. Then what about cathode? At cathode, the connection is between copper solid and Cu2 plus aqueous. So the Nernst equation can be written as E Cu2 plus slash Cu is equal to E0 or E naught Cu2 plus oblique Cu minus RT divided by, again you can see it is 2 electrons. So 2F ln of 1 divided by concentration of, Cu2 plus aqueous. So these are the two equations. So then I hope you have understood till here. Then if we want to calculate for this total one, how did we calculate? Remember, E cell was equal to E of, this was our cathode, minus this was our anode. So okay, you needn't put the brackets out here. If you want, you can put. So E cell, if you want to calculate for the full cell, this is a cathode, this minus the anode, E of the anode. So we have this portion we have here and this portion we have here. So let us put down the two of them. So what can we write for this one? E0 Cu2 plus oblique Cu minus RT by 2F ln of 1 divided by concentration of Cu2 plus aqueous minus of this one. So what is this? This. So it is E0 Zn2 plus oblique Zn minus RT by 2F ln of 1 by concentration of Zn2 plus. So I hope you have understood. We have substituted, using the Nernst equation, we have substituted the values of EZn2 plus Zn and ECu2 plus Cu out here. So this is how it looks like. Then if we remove this bracket, this remains minus and this will become plus. So we have removed the bracket, that is the next step. Then this portion we will club it with this one. So it is E0 Cu2 plus slash Cu minus E0 Zn2 plus oblique Zn minus, can we not take RT by 2F common between these two? So we have RT by 2F and inside the curly bracket we have ln of 1 by Cu2 plus concentration minus ln of 1 by Zn2 plus concentration. So this is what we are having. So this we will apply laws of logarithm, and then this portion we will convert it to this will be plus because this will be minus because minus and minus will become plus. So RT by 2F ln of concentration of Zn2 plus divided by Cu2 plus. This portion, when we combine the two lns, minus sign, this is from the laws of logarithm, that this one will go up and this will remain down and it will be only one ln. So this is this portion. See till here, can we not write E0 cell? So E0 cell minus RT by 2F ln of Zn2 plus divided by Cu2 plus. This portion remains the same, only this portion we have converted into E0 cell. So we have taken the help of this equation to arrive at this one. So what is the total this thing? Let me write it on top out here to be more clear. E0 cell minus RT by 2F ln of Zn2 plus divided by Cu2 plus. That is what I have written down there. Again I am writing because it may not be clear here. So you can see this is the Nernst equation for Daniell cell. So you can see in page 72 they have done for another equation. Please practice that one. They have done for an equation NiS plus 2Ag plus aqueous arrow Ni2 plus aqueous plus 2 Ag solid. This equation is there. They have worked it out also. Please work it out and see whether you can get for this equation or not, this last equation. Then in the same page 72 you will find a general equation written AA plus BB arrow CC plus DD. Now if you look very carefully at the last equation for a Daniell cell, everything here is okay. Or inside the ln, what to write down? Ln of concentration of Zn2 plus. Now if you see this equation, Zn2 plus is your product, and what is below? Cu2 plus, this is your reactant. So always inside the ln you will have concentration term of the products divided by concentration term of the reactant, and here also to the power 1. Why? Because the coefficients are 1. So if you have coefficients like this, then you will raise it to those powers. So here what can we write? E cell will be equal to E0 cell minus RT. We don't know how many electrons are being transferred, so we write NF, general one only. Ln of, now inside this ln what will we write? We will write what are the products? These two, but we will not take the solid because for solid concentration is always 1. So we will write concentration of Ni divided by concentration of Ag plus to the power 2. Now in this case we know nothing, which one is the ion, which one is the solid. So we will write your products are capital C to the power small d into D to the power small d divided by reactant A to the power A and B to the power B. So this will be the last equation for a general reaction. You can see this also has been explained in page 72.